Okay, so we're going to do a bunch of examples using shells, using disks, washers. Sometimes we'll do some of these more than one way. So sphere here, I think we can do it using disks or cylindrical shells. And I think that'd be kind of fun. So notice we just got a word problem here. We're going to derive the volume of a sphere of radius r. We know what the answer is, 4/3 pi r cubed. We're going to prove it. This is where it comes from. It's not like I want you to understand that we're literally proving the formula for a volume of a sphere right here. This is how it's done. So I get to, like, I can pick my picture anywhere I want. I'm going to draw here at the origin some sphere of radius r. How could we generate that? Well, one way might be to take a circle of radius r and rotate it around the x-axis. That could work. Okay. So what's a circle of radius r? Or the upper half of a circle. So the top of a circle of radius r. So the equation for a full circle is x squared plus y squared equals r squared. If we just want the top half, so that's the entire circle. We just want the top half. I want to solve this for y. So you would get y equals plus or minus square root of r squared minus x. This would be the minus. This would be the plus. So we just want the plus. So I've got this curve goes from negative r to r. My curve is y equals the positive square root r squared minus x squared. Positive half of that. Okay, now we're going to take that and rotate it around. Let's rotate it around the x-axis. Ooh, rotate around the x-axis. We get a sphere. Like you know what we're going to get. And I'm going to build disks that live along the x-axis. So I'm going to pick some random x value here, maybe right there. Pick some x value. Now I'm going to have some disk right there. Has some thickness delta x. As soon as I decided I was doing disks along the x-axis, I forced everything to be in terms of x. Then the volume of one of those disks is pi r squared times the thickness. So the volume of that disk is pi r squared times delta whomever we're talking about. What's my r? And like here, I'll say radius is this. It's not always r. Remember, we're not talking this distance. Like look right there, right there. The radius is really small. We're not talking distance from the origin. We're talking distance from the x-axis. So that radius is, oh, just that function there. My delta is delta x. So then the total volume, let's say that'll be pi square root of r squared minus x squared squared. I'm going to have an integral. Delta x or dx, now that we've turned it into an integral. And what am I integrating from? Which x values will I have these disks from negative r up to r? Okay, so that'll be, I could bring the pi out if I want. Integral negative r to r. Square root of junk squared is just junk. antiderivative of r squared dx. Oh, I'm doing the antiderivative now. Antiderivative of r squared dx will be r squared x. Antiderivative of x squared would be x cubed over 3. And that's evaluated from negative r to r. Okay, so let's write all this out. That's going to equal pi. Plugging in an r on top, I'm going to get r cubed, because r squared times r, minus r cubed over 3, minus, now let's plug in, I need parentheses here, plug in a negative r. Here I'm going to get a negative r cubed. Here I'm going to get negative r cubed times negative 1, so plus r cubed over 3. Now I got to distribute this minus. So this will be pi. I mean, I guess we could clean this up. That's, nah, let's not clean it up yet. We got r cubed minus a third r cubed plus another r cubed minus another r cubed over 3. So that's 1 minus a third plus another one minus another third. So that's 2 minus 2/3. That's 6/3 minus 2/3. That's 4/3. We got 4/3 pi r cubed. Huh. Of course we did. We knew that's what the answer was going to be. I keep drawing that too big, too small. All right, now let's do it using shells instead. Think I left myself enough space? I did. All right, so same problem with shells. Now, like we could set this up however we wanted to. If I were going to take the top half here and build shells, like my shells, I would be going from left to right. Those are going to be kind of ugly. Let's kind of think about this. Let's say we had the same setup. I'm going to have to integrate. If I'm going to rotate this guy around, I want my shells to rotate in the same direction. I would be rotating something like this around. And the height of that shell would be this total distance. I would need this guy. See, I would have some delta y. I would need this as a function of y. This is a function of y. And take top minus bottom. Or, because we know we have symmetry here, I could just find this distance and double it. But I would need this here, x equals some function of y. And we could do it. Like, it wouldn't be that much work. But I think it's going to be better if we start with a curve over here and we rotate around like this. So this is the curve, exactly the same curve I was just talking about, x equals square root of r squared minus y squared. So again, doing what we were just going to do, it wouldn't have been that bad. Like, we need this function anyways. I don't know, this is just my first thought when I decided I was going to do the shells, and rotate around the y-axis. So I need my shells to go along like this. But then I thought, working with this, do we really need to go from top to bottom? What if, what if I just did this? Take this quarter circle, rotate it around, either way, x-axis or the y-axis. That's going to give me a half of a sphere. That's going to give me something that looks like this, right? A half a sphere, and then double the answer. So that's my plan. So I'm going to take that guy there that we could either write as x equals square root of r squared minus y squared, or y equals square root of r squared minus x squared. Between, x equals 0, y equals 0, and so and rotate around the y-axis. All right, so what are we going to get? We're going to get some shape here. I kind of already drew this out. We can get in something looks like this. All right, let's draw in a cylindrical shell. So I pick some rectangle, some delta x there that's getting rotated around. So he's going to live like this. So we're building up shells again, like Russian nesting dolls that are starting here at the beginning. We'll have really skinny, tall shells. And as we go out, we'll end up with short, fat shells. Okay, what is the, notice I got delta x. Everybody needs to be in terms of x. The volume of a shell, remember, is 2 pi times the radius of that shell times the height of that shell times your delta, whatever. In this case, we already know it's delta x. I'm at some random location x. The height will be this guy here. That's the height. Notice I need it as a function of x. I can't use this version. Okay, what are my limits here? Don't go from here to here. Remember, this guy rotated all the way around. We just started with a quarter circle. So I only need to go from here to here. So my limits will be 0 to r. So I'll have the volume of the hemisphere, not the whole thing. We're going to double when we get to the end. Will be the integral from 0 to r, 2 pi r square root, 2 pi x. I apologize, because r is x. By r there, I mean radius of the radius of this shell, not the radius of the sphere or the hemisphere in this case. Not this radius, this radius. And then what we got here, square root r squared minus x squared. I do have a point in doing this problem. Okay, to do this integral, I'm going to have to use u sub. So I'm going to have to let u be r squared minus x squared. Then du will be negative 2x dx. And I look and I go, okay, I got my 2. I don't have a negative. I wish I had a negative. So I could put a negative in and take a negative out. Now, this together will be my du. And this will be my u. All right, I got to change my limits. When x equals 0, that will imply u will be r squared minus 0. U will be r squared. when x equals r, we get x squared, r squared, plugging in r for x, we're going to get u equals 0. So I'm going to have the volume of the hemisphere, half of the sphere will be negative integral from r squared to 0. The pi comes along, the 2, the x, and the dx and the negative all go into du. And then this will be square root of u, or u to the 1/2. Now, I don't feel like having this negative out front, and I don't like having my limits be in the wrong order. I like smaller in the bottom. But remember our rules of integrals, I can swap the order here by getting rid of that negative. Okay, well then that'll be pi u to the 3/2 divided by 3/2, which is the same as times 2/3, evaluated from 0 up to r squared. So that'd be 2/3 pi. Well, at 0, that's going to be 0. So I'm going to have r squared raised to the 3/2 power. That'll cancel down and just give me 2 pi r cubed over 3, but that was only the hemisphere. So the volume of the sphere is double that, 4/3 pi r cubed. Now, I'm going to argue that this way was easier. Usually discs are easier. All right, let's do volume of a cone of radius r, height h. I think it's going to be easiest. I've kind of been thinking about this problem. Like I haven't even done this yet. I'm just kind of thinking about it. I think it would be easier if I set my cone up like this along the y-axis. Let me draw him a little better. Maybe I'm wrong. Maybe I still didn't draw very good. Maybe it would be better if I had it the base down here and going up to a point. Maybe. But then, see, I would have like, I don't know. It seems to me like this is going to be more work. I think it's going to be easier like this. Okay, so this will be my radius r here. Will be this top where it ends up. That's the radius r, and then this height is h. We could do this either with cylindrical shells or with discs. I think it's going to be easier with discs. Like, given the choice, I think I'm always going to use discs. Let's check. Maybe I'll use red here. So let's draw in some stereotypical disk up at some height y. He has thickness delta y. So I can see that my y's are going from this is y equals 0 up to y equals h. Okay, now I need the radius, not radius of the cone. I need this radius of that disk there. So I've got some disk here. Here's the y-axis. I need this radius right here. So I need to use similar triangles to figure out what this is going to be in terms of a h and r. So I've got my big triangle here. When this is r and this is h, and then my little triangle here, y was the height. Sorry. This is y. I need this guy here. So I don't know. Let's give it a name. I'll just call it radius of that disk right there. So similar triangle. R over h equals the radius I'm looking for over y. So that radius then will be y times r over h. Why do I care about that? Because the volume of one of these little disks, remember, a disk is just a cylinder with thickness delta y. It's always area of the base times the height. What's the base? It's a circle. So the volume will be pi radius of the disk squared times delta y. And then we're going to add all those up. So our total volume here for this cone will be the integral from 0 to h, because those are the y values for which these disks make sense. Pi radius squared, so I'm going to have a y squared, an r squared over h squared dy. I'm integrating with respect to y. Everybody else is a constant. So I can pull out a pi, an r squared, an h squared, and just have the integral from 0 to h, y squared dy. So that's pi r squared over h squared. Oops. Antiderivative of y squared is y cubed over 3, evaluated from 0 to h. At 0, that guy's going to be 0. So we're just going to throw in an h. We get pi r squared. We get h cubed over h squared, so h over 3. That is the volume of a right cone with base radius r and height h. And we've now proven that. Okay, let's see. This is the last one I got. No, I got a couple more I want to do. All right, this donut problem. Okay, I got this from your book, and they didn't even have the answer. We're going to figure it out. So what we've got here, I'm not sure it's very clear just from the words. So let me explain the problem. I've got a circle of radius 2. That's what that guy is. Got that circle. I'm going to rotate that around the line x equals 4. So take this circle and rotate it around. So right in the middle of my donut here, I should make him dotted, is going to be the line x equals 4. And the x-axis is over here, or the y-axis. Here's the x-axis. Kind of missed there, didn't it? Y-axis, or x-axis would be here. And nope, nope, nope. I didn't even draw it in the right spot. The y-axis would be here, the x-axis would be here, and right there is a circle of radius 2. It's been rotated around. So in this picture, this would be 4 here. That's 4, and that's 2. Okay. Let's do this with let's do it with shells. I think we can do it with shells. Yeah, I think it's going to be nasty either way. Don't think this is going to be a fun problem. That's why it's one of the later problems. So if I do this with shells, I'll pick some random, say, x value here. Pick out this little rectangle. Always draw your rectangle. That is getting rotated around like this. The other half is going to be over here. That height there call that height, and this distance are both going to be kind of complicated. So if this is a distance x here, this radius of this shell I've drawn will be 4 minus x. This distance here is 4 minus x. The height here is going to be the height up to the circle. So that top is y equals square root of 4 minus x squared. The bottom, that curve right there, is y equals negative square root of 4 minus x squared. Top minus bottom is just going to be twice top because of symmetry here. So height will be twice square root of 4 minus x squared. The radius of the shell is 4 minus x. And the thickness is delta x, of course. Okay, for which x values are we using that? Looks like from all the way back here at -2 up to 2. So we would have the definite integral -2 to 2. Let's see, volume of a shell, I always like to write this down, is 2 pi times the radius times the height times 2, and then times delta x, of course. Yeah, 2 pi RH. Okay. So what do we get here? I get 4 pi 4 minus x square root of 4 minus x squared dx. Okay, I'm gonna have to pause and think about how to do this integral. Hold on. Okay, I think we're just going to do this one as let's set up the integral. I mean, we could do it. So what we'd have to do is distribute here. The x times this stuff, it's a u sub. We just did one just like it. The 4 times this stuff, we're going to do a trig sub. Now, back in Calc 1, you may have learned the antiderivative of a square root of a squared minus x squared. We get an arc sign. Like we could do this. I just don't think it's going to be instructive to go through the integral at this moment. Let's just leave it as that's a setup. Okay, let's do this guy here. So that is trying to figure out which one it is we're doing. Number 153. We're doing this one here. So we've got that curve bounded by x equals 2 and x equals 4, and we're going to rotate around the x-axis. So we're around the x-axis, rotating around like this. All right, so we can easily see what we're going to get here. We're going to get some kind of shape that goes like this. We're rotating this guy around. I'm thinking discs. Like we could use shells. Like I could have this thing rotated around. But to do that, I would have a delta y, and I would need this height in terms of y's, not in terms of x's. I would have to go back and solve this function x equals some function of y. If you're integrating with respect to y, everybody has to be y's. That is very difficult. That's not a one-to-one function. Like you would have to say, okay, well, we're only going for x is bigger than 1, so we're going to take this part of the graph. It would be a nightmare. No, shells are not our friends here. We want to use disks. So we still got this guy rotated around. Set up a disk here. So pick some random x value. Here I'm at x. Then this has some thickness delta x, has some radius that. x squared minus 2x. At this location x, the radius of that disk is the function value itself. Volume of a disk is pi r squared times h. What's h? H is my thickness. That's delta x. R is that. All right, then my total volume is going to be the integral. For which x values are we using that kind of disk? From 2 to 4. I get a pi chunk squared delta x. Yeah, it all looks right. Okay, now we just do the integral and bring that pi out. 2 to 4. I got to actually square this out. So to square a binomial, square the first guy, multiply the two together and double it, and then square the last guy. And it's always going to go plus, same sign, plus. That's a dx. Sorry. Once you write the integral, it's a dx. All right, what we got here? Pi. Oh, I think we get x to the 5th over 5 minus, we'll get 4x to the 4th over 4, so just x to the 4. Here we'll get x squared over 2, so plus 2x, evaluated from 2 to 4. All right, I don't think you need me to go through all the little minor steps there. I'm going to just look up the answer. All right, so this is the final answer. And I'm looking at that going, how do we get a 15? Because I goofed right here. 2x squared, of course, would be 4x squared. So this, hopefully you caught that as I was doing it. I like to test you. This guy here, his antiderivative would be 4x cubed over 3. So that's how we end up with a 15 in the denominator, and that is the correct answer. I've double checked it. And that is a good place to stop.